So thank you for the invitation. It's a very nice lecture hall, and it's a pleasure to open this conference. And I will talk about a topic that I've been working on in the last few years, actually pretty much since my PhD, and this is concerned in the broadest sense with all kinds of entropy notions and their applications in cryptography. They slightly changed the title, but it's really not, it's not full screen, right? Control L? No, it doesn't matter. Large enough, right? So this talk, because it's a long 1 hour talk, will be split in 2 parts, and like the red line along the talk will be concerned with the min-entropy, which is an entropy notion that I will motivate and define in a second. And so the first part will be about what many of you probably know as min-entropy, and I will show some cryptographic applications that I've been working on in the last 1 or 2 years with people like Evgeny Dodis and others, mostly about key derivation. And the second part will still be about min-entropy, but now about something that you probably haven't seen before if you're not the cryptographer, namely computational notions of min-entropy. So I will talk about variables that look as if they had a lot of min-entropy, and then we'll see what their cryptographic applications are and how weirdly they can behave in some aspects. So why these computational min-entropy notions are very weird beasts and have very tricky aspects. Okay, so let me start, and let me tell that the first part of the talk pretty much follows the slides that of Evgeny Dodis. So he gave a talk at this Eurocrypt. So when I started doing my slides, I kind of realized that he presented it much better, so I kind of copied his layout. So if you were at Eurocrypt, you will probably see that things look familiar. Okay, so you probably know this guy, Alfred Rényi, after whom this institute is named. So he defined the notion of entropy. This is this notion down here. It's called Rényi entropy of order alpha. And even if you haven't seen this particular notion, you probably have seen Rényi entropy for particular values of alpha, which are very important. In particular, the most popular entropy notion is probably Shannon entropy. It's Rényi entropy of order 1. And Shannon entropy really measures, if you have a random variable, how good can you compress it. So if you have a variable which has k bits of Shannon entropy, it means that you cannot, asymptotically at least, you cannot compress it below k bits. And actually, you even can compress it to k bits asymptotically, and this is a very important notion and mostly used by people who work, for example, in communication and so on, because they really want to know how much bits do they have to send over the channel in expectation to kind of transfer one variable to the other. Now, in cryptography, we often don't use Shannon entropy for the following reason. You can have a variable that has like 2 million bits of Shannon entropy, but it can have the following distribution. It's a 2 million bit string. With probability 1/2, it's uniformly random. With probability 1/2, it's the constant 0 string. Has 1 million bits of Shannon entropy, but it will be completely useless for cryptographic applications because like half of the time it's just nothing. So you cannot use it as a key, you cannot do anything useful with it. There is no secrecy in it. That's why in crypto we typically are much more interested in something that is called min-entropy, which is, again, Rényi entropy as alpha goes towards infinity. Is defined like this, and instead of looking at this definition, it's much more interesting to see what it actually means. If you have a variable that has k bits of min-entropy, it means that no particular value has probability more than 2 to the minus k of appearing, right? So if I have a variable, I don't know anything about it, I know it has min-entropy 100, then I know that there is no particular value that will show up with probability more than 2 to the minus 100. And this is, of course, much more useful in cryptographic applications because we know that, no matter what the adversary does, he cannot guess the outcome of this variable with probability better than 2 to the minus its min-entropy. And so this will be the notion that I will be talking about. And so these are the standard definitions of Shannon and min-entropy, and especially for the second part of the talk, we can also look at conditional variants of this entropy. So this is conditional Shannon entropy, and this is conditional min-entropy. And again, if you define it like this, what it means is that if x conditioned on y has Shannon entropy k, this means that if somebody samples this joint distribution xy, he gives you y, so y is public, you still need k bits to describe this variable x. And similarly, so this particular notion of, which is called average case min-entropy, captures the fact that, again, you sample to a joint distribution xy, you are given y, and given y, you cannot guess x better than probably 2 to the minus the average min-entropy, on average. So there could be particular values of y for which you can guess better or worse, but on average in this game, you will not be better than 2 to the minus k, and this turns out to be the right definition for cryptography. And as you see, it was only defined like 6 years ago. And before there were different worst case notions, but this is really the most convenient one to work with. So whenever I will talk about conditional min-entropy, I will mean this definition here. So what is min-entropy good for? So when we construct cryptographic schemes, you want to write a crypto paper, you say, okay, I'm going to make a new encryption scheme. Then you define all these primitives, key generation, which takes uniform randomness, outputs a public and secret key, and everything else. But almost every time, what you will start with is, I pick uniform randomness at some point to sample the key or whatever. And yeah, so this is this theory line. So this is like the theoretical setting that we are typically in if you write a crypto paper or if you think about cryptographic primitives. But what happens in practice is, more often than not, you probably don't have really uniform random bits coming for free. Okay, but what you typically have is some kind of source that gives you some kind of randomness that has some entropy. For example, in biometrics, it would be a fingerprint, or maybe you have some kind of random number generator in your computer that kind of takes keystrokes and generates some distribution. And this distribution will not be uniform, but you can reasonably hope, probably, or maybe you guarantee that at least it has some sufficiently high min-entropy. And the task of key derivation is simply the task, given such a source, x, which has some kind of min-entropy, derive a good key. And derive this good key by means of some function h that you apply to this source, and you hope you get the good key out. Right? Very simple task. So that's what I will talk about for the next 20 minutes or so. Okay. So again, so this is the ideal model. Ideal model, you have the primitive, uses uniform randomness. Reality, we have some key k that we have derived by means of some key derivation function from some source x. And what we want to do is, now we want to do the following. The challenge is the following. Assume that our primitive is epsilon secure, whatever that means. I will show you later. Maybe no adversaries of some particular size can forge you signatures with probability better than epsilon. So epsilon is kind of typically sort of very small value that kind of bounces security against some particular class of attackers. So in the ideal world, when using uniform randomness, it's epsilon secure. And now we want to prove that our scheme still remains epsilon prime secure in the real model. So real model means the key is derived from this high min-entropy source if we use this key k. And the question is, of course, how small can this epsilon prime be? And of course, it will depend on, of course, of the epsilon we start with. We cannot hope to beat the security in the ideal model. And probably it will also depend on the amount of min-entropy that we have, and on the length of the key. So the amount of min-entropy will always be denoted by k, small k, and the length of the key will always be denoted by m. So these three parameters kind of, how good can epsilon prime be as a function of this? And in particular, to make two more concrete questions, we can ask the following questions. If we want the security in the real model, epsilon prime, to be roughly the same as epsilon, say not more than 2 times epsilon, right? Same order of security, how large must k be? So, k is the min-entropy of the source. Probably k will have to be at least as much as the length of the key, because of the uniform randomness that the ideal primitive uses, because the ideal primitive has m bits of min-entropy, so we cannot hope to beat that, but the question is, how close can we get? So an alternative point in this parameter space we could ask for is, okay, what happens if our source actually has exactly the amount of min-entropy? Then we would require from this uniform, perfect m-bit key. So if k is equal to or almost equal to m, how good epsilon prime can we get? So I will actually discuss these 2 points for several settings. So what is done in practice? So in practice, what happens is, practitioners, they have to write this cryptographic software. They get some kind of distribution out of maybe the computer hardware or from keystrokes or something like that, and then they have to derive the key. And what they do is, they just apply some cryptographic hash function, say SHA-3, to this source, and they get out something, and they hope that this is as good as a uniform random key. And so how is this justified? So they say, okay, what you can actually prove is if we assume that this cryptographic hash function behaves like this magical random oracle, so like a uniformly random function that suddenly appears in the sky, everybody has access to it, and we apply our source to this uniformly random function and get our key out, then you actually can prove very, very, very good properties of this key derivation. It's perfect in almost every sense. So if you have a key of length m and let's see, Oh yeah, so what the security epsilon prime we get is, it's at least epsilon, which is the security of the original scheme, plus epsilon times something exponential in length of the key minus the entropy of our source. So even if m equals to k, so if we have as much entropy in the source as we need for the key, epsilon prime is upper bounded by 2 epsilon. Very good. Right, so dream version. And the question is, how, of course, random oracles don't exist. So the question is, what does this imply for actual security in the real world? And one can say, actually, this very heuristic argument is actually surprisingly solid, in the sense that I'm not aware of any case where one used a strong cryptographic hash functions for some natural scheme, and with some natural source that had sufficient high min-entropy, and things went fatally wrong. But still, there is valid criticism about the scheme. It can, at least in the artificial setting, go wrong, I guess. And the question, one would like to know, for theoretical but also for practical, is this: how close can we come to this ideal world provably? Right? So with not making any weird assumptions about magical functions in the sky. So really improves it. So during this talk, I will come up with this table, and it will grow. And this table has a few entries. So this table will compare the different approaches for key derivation. So what I showed you now is, okay, if we use a random oracle, we use a cryptographic hash function and think of it as a random oracle for any application. It has to be not any application. It doesn't work for information theoretic cryptography where adversaries are computationally unbounded, because then they can just learn the entire function table of the random. But like for computational applications, as we care in practice, and then we have like these entries here. So this last sentence just says, there is no provable security guarantee, but what we can hope for is security. Yeah, that's what I said before. If the min entropy is the key length to epsilon, the entropy loss to get, it's a bit redundant now, but it will make more sense for other. So if we want epsilon prime to be upbounded by 2, that's the entropy loss. So the amount k minus m. K is the entropy we have in our source, m is the key we want. And k minus m, I will call this the entropy loss or entropy gap. This is kind of what we waste, what we have to waste in order to get the security of the same order as the original scheme. In this case, it's really 0. So we don't need any more entropy in the source than we need for the key. Okay, so we'll come to this figure a few times in this talk. So what can be provably done in terms of key derivation? So there is like one very standard technique developed in the 80s, 90s, and it's called the tool that is, 90s, by Nielsen Zuckerman. It's called the strong extractor. So what is a strong extractor? A strong extractor is a function, and this function has 2 inputs. It takes some value x, some value x, and then additionally, it has to take some it has to take some seed that we assume is uniformly random, and it has to be independent of x. And what this extractor guarantees us is the following. If this source x has sufficiently high min-entropy, so we call it a delta k extractor if the following is true. Whenever we have a variable x that has at least k bits of min-entropy, the output of the extractor on input s and this uniform random seed is delta close, statistically delta close, to uniformly random, even given the seed. So this is why it's called a strong extractor. This is a strong extractor, and you already see, this is of course very good for a key, as a key derivation function. There is a caveat, so you kind of need this uniformly random seed, but typically you can just generate it once and hard-code it somewhere in your hardware, and then you just hope that whatever that the source that you have is independent of this value. And there is, if you model things correctly, you have good reason to believe that. Of course, the question is, do strong extractors exist? Oh no, sorry, before I address this question, let me say, why is this a good key derivation function? Yeah, so there is a statistical distance has a very nice property. If you have some game, some experiment, it involves some variable x. Let's not call it x, let's call it k. It involves some variable k. And you replace this variable k with something that is epsilon close statistically to this variable, then this entire experiment, every variable, everything that comes up is also going to be epsilon close to this original experiment. In particular, if your scheme is epsilon secure with the uniform key, so this game that defines security will kind of output the adversary 1 with probability epsilon, it will be still epsilon plus delta secure if you replace this uniform randomness, um, with some key k that is statistically delta close to it. For example, you replace this uniform randomness with a key K that has been extracted from some source X using a strong extractor. Right, so you can do this, and this already solves our key derivation problem. The question is how good extractors can get, if we talk about concrete parameters. And then there is a very famous paper by Kostadin, Baliazzo-Lubin-Levin. Actually, it's from '86. This is the journal version, so it's a very classical paper. And they show that universal hash functions. So universal hash functions is a family of hash functions that that map to some domain, and the probability that if we pick a family from this function uniformly at random, the probability that they will collide if applied to this function is basically 1 over the domain side. And so I will not go into this, or pairwise independent hash functions, for example, are universal hash functions. So they showed the following interesting fact. So if any universal hash function is a delta K extractor, where delta is this value here. So let's look at this for a second. What does that mean? So of course, extractor means we have this family of hash functions, and the seed of the extractor S tells us which member of this family to pick, and then we apply this function to this source X. So how good is this delta? Let's see. So this is the distance. So if the entropy of our source is the same as the output length m, K equals m, then the statistical distance we get, okay, 2 to the 0, 1. So we have absolutely nothing. So the statement is void in this sense. It guarantees absolutely nothing. So to use strong extractors for key derivation, we need a source which has at least somewhat more min-entropy than the output key that we want. In particular, if we want this delta here to be of some order, to be epsilon, some epsilon, this epsilon will be the security of our scheme for which we want this, to use this key. So we want delta to be epsilon, so that the overall security will be epsilon plus delta, roughly 2 epsilon. In this case, this entropy gap K minus m has to be 2 log 1 over epsilon. What is the typical epsilon that would appear in practice? Maybe you want 2 to the minus 60-bit security. That's already pretty conservative. Pretty low security. Typically, epsilon would be something like 2 to the minus 100. So in this case, this entropy loss would be like 200 bits. And let me come to this in a second. So this would be 2 to 200 bits. And in many settings, this is simply not an option. For example, take biometrics. I think a fingerprint is assumed to have roughly 160 bits of entropy. So if you lose 200 bits, there's, you have minus 40. So there's really, in many settings, this is just too much. The question is this optimal, or how good is this extractor? No, this is a paper from '86. This was pretty much the first extractor. So what are the improvements? Actually, none. There is a paper by Radhakrishna and Tashma who show that actually already these very simple universal hash functions are perfect extractors, in the sense that this delta has to be at least what the leftover hash lemma gets for any delta K extractor. So there has been tons of work on strong extractors since, but those work actually was concerned with getting the length of the seed that is used to extract, to make that seed shorter and shorter. Not to improve this bound, because, yeah, we can. Okay, so as said before, often we cannot simply lose this 200 bits, or often we don't want to lose this 200 bits because we could if we wanted to. So one applications of key derivation is, for example, if you do Diffie-Hellman key agreements, so we agree on a Diffie-Hellman key. Now we don't have really uniform randomness. We have some kind of element in the group that has some kind of actually it has computational min-entropy, but looks as has high min-entropy. And if we lose all this and because we lose this 2 log 1 over epsilon, we have to actually start with very large security parameter for our Diffie-Hellman key exchange to start with, to get some kind of reasonable security guarantee. Okay, so this is the second line in my matrix. So now I showed you how to do key derivation for absolutely any application. What is the function? The function was a universal hash function, so using the leftover hash lemma. What is the security loss? Sorry, let's see. What security do we get if the min-entropy is the same as the key length? As said before, absolutely none. How much do we have to lose if we want to get security roughly of the order as the original applications? 2 log 1 over epsilon. So, but this is provably secure. Okay, so the question now comes, can we improve on that? And So I told you that we cannot beat this RT bound. So if we want to do better than what I just showed you before, we have to find another strategy than the strategy that I showed you before. So the strategy I showed you before is, okay, we have epsilon security with the uniform key. We make sure that we get the key that is delta close to the uniform, and we get epsilon plus delta security. But maybe that's overkill. Maybe we don't need a key that is statistically close. Maybe we can either fiddle around and get away with something weaker, or make some additional assumptions and do better. And so the first answer is, in general, that's not possible. So there exist applications where really, okay, so one approach that you want to take is the following, and that we will take in this talk, is, okay, we really wanted the key that is delta close to uniform, but maybe that's overkill. Maybe it's enough if our key is not close to uniform, but just has very, very high min entropy, maybe m-1. It will still have statistical distance 1/2. It's very far from uniform, but it has very high min entropy. Maybe that's sufficient for crypto applications. And in general, it's actually not, unfortunately. So here's a very simple example. Consider a pseudo-random generator. So this is a function that takes an m-bit string and maps it to a 2 m-bit string, and it has the property that when you choose this m-bit string uniformly at random, this 2 m-bit string is indistinguishable from a uniformly random string. So it generates something that is longer than its input, and the output looks random if the input was uniformly random. Now consider the following distribution of keys. We pick all keys where the pseudo-random generator output starts with a 0. And then we take a key uniform over this set. What is the min entropy of this key? It's very high. It's roughly every second key. So the min entropy will be m-1, very high. But what is the security of the pseudo-random? Security for pseudo-random generators means the advantage of an adversary in distinguishing the output of a pseudo-random generator from uniformly random. But of course, if we pick this particular key, then the security is gone, because if you get the pseudo-random output on any key in this set, you know it starts with a 0, and you can distinguish with very good probability from uniform random string, which will start with a 0 with probability only 1/2. So it's not going to work in general, but I'm going to show you that it works for many interesting cryptographic applications. And the applications for which it will work are so-called unpredictability applications, and they include, for example, digital signatures, message authentication codes, and in general, they include all applications which can be very roughly described by a game, where the security experiment is captured by a game, and the game goes as follows. The game gets some uniform randomness, it's a probabilistic game, and we say that the application is epsilon secure for some class of adversaries if for every adversary the following is true. So this game takes this adversary, picks some randomness, and then plays this game with the adversary, and at the probability that at the end it outputs 1, which means the adversary won, is bounded by epsilon. A concrete example, digital signatures. So the game gets uniform randomness. It uses this uniform randomness to pick a public and a secret key. It gives the public key to the adversary, and the adversary can make signature queries, and at the end it tries to come up with the valid message signature key that it has not asked explicitly before, and if the adversary manages to do so, we output 1. And security of a signature scheme says the probability that the adversary output 1 is very, very small, negligible. So this would be an unpredictability application, and this is in contrast to, for example, indistinguishability application, like the pseudo-random generator I showed you before, which was captured by 2 games, G0, G1. And again, so one game was like the real randomness, so this would be here, and in the other game, the adversary would get the output of a PRG on a uniform string, and it should not be able to distinguish those 2 games with probability epsilon. But in each game, it can output 1 with high probability. The probability should just be very similar. So if we make this, so this is indistinguishability applications, pseudo-random generator, pseudo-random functions, semantic security for encryption schemes, and so on. This is unpredictability applications, yeah, digital signatures, message authentication schemes, and many others. Yeah. Okay. And here is a very simple lemma, very simple observation concerning unpredictability applications that does not hold for indistinguishability applications. Assume you have some unpredictability application, and it's epsilon secure with the uniform key. What happens if now instead of a uniform m-bit key, you just have a key that has m, the key has still length m, but it only has m minus l bits of min entropy. L, think of L as something small, like 1 bit, m minus 1 bit. We've seen before that for pseudo-random generators, this completely kills the application. But not for unpredictability applications. In fact, you can show quite easily that if the original scheme is epsilon secure with a uniform key, it remains epsilon times something exponential in this entropy gap, epsilon times 2 to the L, if we use any key that has sufficiently high min entropy. And what is the intuitive reason? So here's the proof, but like, what is the intuition here? So think of this as the set of all possible keys. This is the uniform distribution. We have this high min entropy distribution. So think of it as a flat distribution, some subset of keys. And we know that, and assume an adversary breaks the scheme with some probability delta if we pick a key from this set. And we want to make a statement about what is the probability that he breaks the scheme. Well, what does it mean he breaks it? It means the game outputs 1 with probability delta if we pick a key from this set. But if we now pick a key from the big set, which is 2 to the L times larger, then actually we can simply condition on the event that if we pick a uniform key, we actually land in this smaller set. This will happen with probability 2 to the minus L. And conditioned on being in the smaller set, we will output 1 with probability delta. So that's kind of how this loss in 2 to the delta comes in. And this completely doesn't work for indistinguishability applications, but it works for unpredictability applications. So this kind of suggests a route to construct much better key derivation functions for unpredictability applications. Not for all applications, but just for unpredictability applications. Because now, instead of any strong extractor, we just need a weaker object that is called the condenser. And the condenser, so a KL epsilon condenser, is a function that does the following. So again, S is a uniform random seed and independent of X. It has the probability that if we invoke this condenser on some variable X, which has sufficiently high min entropy, K, so this is the first parameter, then what we get, this output comma S will be statistically epsilon close, so this epsilon was this third parameter, to some other distribution, joint distribution YS, where Y has high min entropy. Okay, forget the epsilon for a second. So if this epsilon was not there, a condenser would simply take X, and if this X has sufficiently high min entropy, it will output something that is much, much shorter than the original X, so it condenses it down. But what it outputs is not uniformly random, but like has very high min entropy, maybe m minus 1 bit or something like that. But this little fiddle room, this L, which can be 1 bit. Oh, and if we set L2 equals to 0, we actually get back the notion of strong extractors that I showed you before. But allowing for a non-trivial L, even just L equals 1, will allow for massively better parameters. And this epsilon is here to give us a little bit. Okay, ignore this epsilon for now. Okay, so here is a theorem from this year's Eurocrypt that I have with Evgeny and Daniel Wicks. It basically says that we can construct very good condensers. So what are the parameters? It says that, first of all, what is the function? So for strong extractors, I told you that just pairwise independent, universal hashing or pairwise independent hash functions will be enough. Here we need something slightly more complicated, a log delta 1 over delta wise independent hash function. So this is a function where you pick a member from this family, and if you a k-wise independent hash function is a function where you pick a random member from the family, you evaluate it on k points, and all these k points look output to uniformly random. For example, you can take a polynomial of random polynomial of degree k, and that will give you such an object. Okay, hash functions. Okay. So the condenser has the following property. So this is the theorem, but maybe this very last thing is the interesting part. It says that if we start with the variable X that has min entropy m plus, so we call that for strong extractors, we needed the gap of log 1 over epsilon to get epsilon close to uniform. Now, if we, instead of setting L equals to 0, we set L equal to 1, so we just want something that has a key that has m minus 1 bits of min entropy, we actually need a much, much lower entropy gap, namely the entropy gap, so what we need more on, what we will lose on entropy while condensing is only something like log. So W logarithmic in this security parameter. And you know, log is less than 6 if you put the number of atoms in the universe. So this is really a small constant actually. And okay, I can show you how this theorem is proven on a very high level. And it's proven using a balls and bin game. I think you've seen that. So this is an experiment that comes up in many different areas of math and theoretical computer science. And it considers a game where you simply have some bins and you throw balls into the bins. Let's say for now you throw them uniformly at random. Later we will have to throw them differently. So this is like some picture I found on the internet. And so this shows like the distribution, what happens. So here's like 100 balls and 100 bins. This is something, 5,000 balls in the same number of bins. And you see what happens. The more balls you throw into, the more evenly distributed this distribution gets. If you throw many more balls than you have bins, then you get like almost a uniform distribution of number of balls per bin. Whereas if you throw only very few, you have like this noisy thing. And now we can think of extractors. You can actually think of a strategy of throwing balls into these bins where the distribution you get is almost uniform. So the fact that you need a large entropy gap simply comes from the fact that you have to throw so many balls to kind of flatten this distribution out. And the leftover hash lemma says you don't have to throw them uniformly at random, it's enough to throw them pairwise independently somehow. And you get this distribution. Whereas the condenser, so the theorem I showed you before, corresponds much more to this case. It tells you that, okay, now we have like this entropy gap, so maybe we don't want to be uniform, but we want to have a cap on the min entropy. So we kind of, instead of cutting off here, we kind of cut off slightly more above. Let's say we have an entropy gap of 2. So this will allow us 4 times more balls, so we would cut off here. Okay, then there is still this outline, but I said before, we only want to be epsilon close to uniform. So it basically says we only have to throw as many balls to make sure that if I throw in the epsilon fraction of the ball that had highest, epsilon fraction of the bins that had highest weight, what I'm left with is kind of at most 2 to the L times what you would expect. So this is like what I just said. So this is this experiment, and this is fairly easy to analyze if you assume that the balls are thrown uniformly at random. You can make a simple calculation, and then if you work a little bit hard, you can actually show, throwing these balls using a log 1 over delta-wise independent hash functions will give you basically the same bounds, and that's how you prove that this 1 over delta-wise independent hashing is a good condenser. Okay, so this gives me the third line. So this was before, strong extractor. So now for any unpredictability application, so if you know you want to get the key, and you know for what you're going to use it, I'm going to use it for a message authentication code, unpredictability application, then in fact you can use log 1 over epsilon-wise independent hash functions, and you get the same security as you would have basically, 2 epsilon, what you would get with uniform randomness. And the entropy gap, so the min entropy you need from your source from which you extract, is only something like log 1 over epsilon bigger than your key length. And it's provably secure. And I left one line out here, so this is something I will not talk about. I now talked about any applications and distinguishability applications. And there is like a very cute, interesting class of applications that are called square-friendly. They include all unpredictability applications, but also others. For example, public key encryption or weak pseudo-random functions, which are pseudo-random functions that look random if queried only on random inputs, not adversarially chosen. And for the square-friendly application, so this is mostly work by Evgeny Dotis and Yuyu, and so we started this in this paper by Barakatal, we get like something interesting in the middle. So with the leftover hash lemma, we had to use 2 log 1 over epsilon entropy. Log 1 over epsilon is something like 80 bits, so it's considerable. For square-friendly, you can get rid of this 2. You just lose half as much. And for unpredictability applications, you basically get down to a constant 6. Actually, it's 6 plus, so it's log plus 4 to be precise. But basically, you get it down to a very small constant. So here's like a very concrete parameter setting. For example, assume you want to use the CBC max. So this is a message, this is a mode of operation. It takes a block cipher and turns it into message authentication code. Say we use a block cipher with 128-bit keys. And say we consider adversaries where the security that we get will be something like 2 to the minus 64. Like a reasonable set of parameters. And now we want to derive a key, and what we want is really the derived key, the security should really be basically the same as we get with the uniform key. So with the leftover hash lemma, what we needed was, okay, to get epsilon prime less than 2 to the epsilon, we needed a source that has twice as much min entropy as this m, namely m plus 2 log 1 over epsilon, 128, plus 2 times 64. We need 256 bit to get the key to get a good key. With these condensers, using the fact that actually we have unpredictability applications and using this not pairwise independent hashing, but this almost 1 log 1 over epsilon wise independent hash functions, we only need 138. Right, so there's like this plus 4, which comes up in the proof. This is this log 3. So we are up to 10 bits, we are as good as the random oracle. Okay. Okay, that's what I just said before. Okay, this was like the first part of my talk. How much time do I have? When did I start? Okay, perfect. That's very good time. Okay, so maybe now any questions to this first part? So this was about min-entropy and key derivation from min-entropy, and now I will come to the second part, which will talk about computational notions of min-entropy. So like variables that look like having min-entropy. Everything clear? Okay, good. Let me continue. Okay. So I will talk about the very simple, or something that you probably learned in information theory. There is something that is called the chain rule, and that holds for almost all entropy notions, and probably all entropy notions that you have encountered. And it's a very intuitive fact that says the following. If you have some variable x that has entropy k, min-entropy, Shannon entropy, whatever, right? It has entropy k. And now you condition on some, think of A as something short. You condition on some extra short auxiliary information, L bits. So somebody gives you this information. And then the question is, how much entropy is left in X if I condition on this short L bit string? And intuitively, because you just get a little bit of information, the entropy should just drop by a little bit. Because entropy kind of captures the uncertainty about X. So if you get something short, the entropy should drop by at most X. And there are many chain rules that kind of have this kind of form, right? So if you have the entropy of X condition on A is at least the entropy of X minus the length of that part I condition on. So in particular, there's this very nice chain rule for Shannon entropy. There is this chain rule for min-entropy, and it holds. It's actually even stronger than what I have up here, because this is max entropy, not min-entropy, but this is of course only better than this here. Okay. And you can ask the same question in the conditional setting. So now you have a variable x that conditioned on some variable y has some entropy, and now on top of that you get additional information. And in the information theoretic case, this really doesn't matter. It's exactly the same chain rule hold. Okay. So this is just to set up some notation for the rest of the talk. So I already defined statistical distance. And let me now also define computational distance. I will write x and the subscript epsilon s y if x and y are random variables that cannot be distinguished by circuits of size s. I think adversaries running in size s with advantage more than epsilon. In particular, if s is infinite, then we get the notion of statistical distance. And I will just use this tilde to say that they are identically distributed. And in cryptography, it's often convenient to have asymptotic security notions. So if I have like ensembles of variables, so x1, so variables that are defined by a sequence of typically longer and longer variables, x and y, then I say that these distributions are computationally indistinguishable if they are epsilon n, s n indistinguishable for some where epsilon n is negligible for every polynomial n. So this is like standard notation in cryptography. We basically want to say that as we take bigger and bigger n, they become harder and harder to distinguish, and harder means any polynomial, even if the adversary can grow polynomially in n, his advantage in distinguishing will drop faster than any polynomial. Just think of them as, very hard to distinguish. The exact definition is not so important. And one notion in cryptography that is tremendously useful, has been introduced in the 80s by Mikali and Yao, is pseudorandomness. And we say that the variable is pseudorandom if its computationally distinguishable from the uniform random distribution. So I already told a little bit before about pseudorandom generators. These are functions that take a short uniform random seed, map it to something longer, and the output is pseudorandom in the sense that it cannot be distinguished from something uniformly random. Now here is so this is the definition, right? So x is pseudorandom if x is computationally distinguishable from the uniform distribution, right? So U is like this is the ensemble of uniformly random strings of length n, and x is like this pseudorandom distribution somehow defined. Here is the alternative definition. It's exactly the same definition, but it's kind of more complicated. I can say that this ensemble x is pseudorandom if it's indistinguishable from some other ensemble y, where yn is of length n and has, let's say it has min-entropy n. Why is this the same? Yeah, the only variable of length n that has min-entropy n is the uniform distribution. It's exactly the same as above. But now if I have this definition, I can kind of start fiddling with it. I can say, okay, what if I replace this n with something that is potentially smaller than it, say n over 2. And then we get the notion of pseudo-entropy. In particular, I can say that this variable x has pseudo-entropy k. So this is some function of n. So think of it as n over 2. If it's indistinguishable from some other distribution, ensemble of distributions, where this other ensemble has true entropy, k of n. So this strictly generalizes this notion of pseudo-entropy to pseudo-randomness to pseudo-entropy. And this, considering such notions, this has been done in this Hill paper in '86, but then the construction of for constructing pseudo-random generators from one-way functions, but not many more applications have been found for like 20 years. But like in the recent few years, like a bunch of applications has come, like leakage resistant cryptography, which is something why I started to look into these things, and many others. Okay, so let me make this more formal. We will say that the variable x has k bits of Hill pseudo-entropy. So Hill comes really from this original paper, if it's indistinguishable from something that has the same amount of min-entropy. Right? So this is the definition. So we say x has Hill entropy k if x is indistinguishable from some y. And you see this, if we define this pseudo-entropy, we not only have to define the amount, k, but there is also like this qualitative parameters epsilon s. So we say x has k bits of Hill entropy of quality epsilon s if it's indistinguishable from some variable that has min entropy k against this, epsilon s distinguishers. So no distinguishers of size s can distinguish this. And again, we can define the conditional case where we simply say that x conditioned on z has Hill entropy k if it's indistinguishable from some other distribution yz, where y conditioned on z has min entropy k. Okay? Now, this definition that I just showed you is also called, so has been introduced by Xiao et al. I kind of consider that's the standard definition of conditional Hill entropy. But, it's not, if you think about it, you could define it differently. For example, before what I required up here is that the marginal distribution of x and z and y and z is the same. Like x conditioned on z has high Hill entropy if there is other distribution yz, where this marginal distribution on the second part is the same, where y has very high min entropy. But I could drop this requirement. This has been done by Gentry and Wicks, and they call this notion relaxed Hill entropy. So it's only really different here. So now I still want indistinguishability, but it does not have to be information theoretically the same. So z and w, of course, have to be indistinguishable because these joint distributions are indistinguishable, but they don't have to be identical. And they used this result for a very nice impossibility proof, showing that no black box construction can construct very compact computational proofs. Another, I think this is by Canetti et al. Another notion is called sampleable Hill entropy. Here we just take the original notion, and on top of that we require that there exists an efficient algorithm that samples this distribution y. Why did they do that? Yeah, because that's exactly what they needed for the application, and okay, they define it. A third notion, decomposable. So here you need that x has high Hill entropy condition on any particular outcome of z. It's not important that you know this, that you kind of get the intuition for all these notions. Just let me say that there are many conditional notions because they came up in many different applications. And these notions are kind of, so sampleable and decomposable seem to be incomparable. Both of them imply standard, which means that if you have k bits of sampleable Hill entropy, you have k bits of standard Hill entropy, and this implies k bits of relaxed Hill entropy. The other direction seems not to be true. Okay, so, funny notions. And of course, now we can ask the question that if chain rules hold for this kind of conditional Hill entropy notion. So is it true that if something has x has some Hill entropy and I leak something, do I still get something that has high Hill entropy? Okay, so let me remind you this chain rule here. So this was the chain rule for min entropy. So we know that if x has some min entropy k, we give some L bit string a, the min entropy drops by at most L. And in fact, the same has been proven actually fairly recently, 6 years ago. Here is the standard notion of conditional Hill entropy. And I can give you intuition why it's probably hard to prove a chain rule for computational notions of entropy. Because consider a pseudo-random generator, so it has like a short n-bit seed n, and it maps it to something very long. Let's call this x. And by definition of a pseudo-random generator, the Hill entropy of x is large. By definition, this is indistinguishable from uniformly random. Uniformly random, so it has its Hill entropy is, you know, the length of this thing. But what can you say about the Hill entropy of X if I leak, say, n bits? Let's say I leak n bits, and what I leak is actually this seed S. Now everything's, you know, everything is off. So if I'm given S, I actually can compute X myself, and of course X does not look like something that has high min entropy because I can distinguish it from every other value. So this is going to be 0. Even if I start here with, like, you know, even if I start with very strong, high quality entropy here. So we cannot hope to get a very, very good chain rule for we cannot hope to get a very good chain rule for Hill entropy, but what we can hope and what can actually be shown is that the chain rule holds. But what happens is that epsilon prime s prime, you not only lose, so here's the chain rule, you not only lose in the amount, so if I condition on some variable x, I not only lose in the amount, but I also lose in the quality. So against the set of distinguishers that I can distinguish. So this chain rule here is not going to be a contradiction to this, because it basically says, okay, if you really condition on something that has n bits, then the security will drop by so much that it becomes meaningless. But if you only, but what this theorem says there is that if you only leak, say, a few bits, you know, whatever bits, any 10 bits, can be some bits of S, can be any function of S, then it says that what you get, that X conditioned on these few bits, still will have very high Hill entropy, of somewhat lower quality, but the quality drops something like exponentially in the length of the bits that you leak. So it's kind of the best you can hope for, and actually this is true, and this chain rule is tremendously useful. So this fact is very useful. It has been used, you can get an idea why it's useful. Already with this PRG settings in leakage resilient cryptography, for example, we care about keys on some devices where an adversary gets some side channel information about the inner workings. So he might get some information out about this seed S, but you can say, okay, as long as this information is not too much, the output still will look as if it had very high entropy. So you can kind of continue working with that. And this is how leakage, some of the leakage resilient stream ciphers and other symmetric crypto schemes are constructed using this chain. Okay. So this chain rule is proven actually using there is a proof that uses the min-max theorem. There is another one that uses ergodic theory. So this is, and apparently the green Tao paper proving the infinite progression of primes uses something very similar. So actually we computer scientists didn't understand what they are doing, and they didn't understand what we are doing, but there is, I think, now a paper by Gowers who kind of explains the relation. So if you want to look into that, it's actually nice math. Okay, so having shown the chain rule, you know, here I started with the variable x, I conditioned on some short a, and I showed that what happens is that really the Hill entropy drops by at most L, and the security degrades somehow exponentially in this in the length of this conditional part. But I started with the variable x. Now I can ask myself, wait, what happens if I start with x conditioned on some other y? So I have x conditioned y has some Hill entropy k. I leak one bit, say, what happens? How much does the Hill entropy degrade? And okay, in the information theoretic case, you know, the chain rule still holds. And this chain rule also holds for many other computational notions of entropy. It has been proven for Yao entropy and unpredictability entropy, which I did not define in this talk. It has also been proven for Hill entropy, namely for the decomposable, sampleable, and the relaxed notion in different papers using different techniques. But somehow weirdly, so it has been proven for this weakest notion. It has been proven for the strongest notions. But somehow weirdly, nobody proved it for the standard notion. It was kind of, people just thought probably it's a hard proof, yeah? And weirdly enough, it's wrong. So this is kind of something that I'll give you the motivation why we looked into this later. But weirdly enough, it's wrong, and it's wrong in a very strong sense. So there actually, you can come up with distributions x, y, such that x condition of y has tons of Hill entropy. So this x is indistinguishable from some variable with very, very high min entropy. But if I condition on a single bit, I just give you one bit, everything's off. The entire entropy is gone. It's very counterintuitive. And I will show you the proof of this thing, and you know, in retrospect, you kind of see, that's why this weird behavior comes up. Okay, this is probably a bit of overloaded slide. Maybe I would just want to tell you, before I show you the proof of the intuition for the proof of this theorem, so why did we look into this? So what happened is, we were working on a problem that is called deniable encryption. So this is something that has been suggested in the mid-90s by Dwork and others. And it's an encryption scheme that has a very nice property that if I encrypt something, I can later, come up with a different explanation for what I sent. So you can kind of, if you get coerced, you can kind of say, no, I didn't say put into prison. I sent the mail, hello, how are you? This deniable encryption, it was like a very natural notion, but nobody could come up with it. And we realized at some point, while trying to construct these deniable encryption schemes, that if we had one, that if we could prove the chain rule for conditional Hill entropy, then deniable encryption would not exist. So we were very excited. We thought, okay, no, that's the route to kind of prove why nobody showed deniable encryption exists in over 20 years, simply because it's wrong. So we just have to prove the chain rule. And once you start really working on this chain rules, at some point we realized, okay, actually the chain rule is wrong. And what happened very recently, last year, there were actually now candidates for deniable encryption. So that's using indistinguishability obfuscation, like a very new tool that came up last year. People actually have the first serious candidate for a deniable encryption scheme. So the chain rule is wrong, and if it had been true, then deniable encryption would not have existed, but it seems that the reality is that deniable encryption exists. Anyway, I think it's a nice route. And another question is, if the chain rule is wrong for conditional Hill entropy, then the question is really, maybe this is the wrong notion of conditional Hill entropy. And I don't have a good answer for that. It's simply the case that it really seems to depend on the application, what kind of conditional notion you have to use. Okay, but what I will do now in the last 10 minutes or so that I have is I will give you an intuition and a proof sketch how it is possible that one single bit destroys all the Hill entropy tables. So you have okay, so I need like a few definitions. The first is a one-way permutation. A one-way permutation is simply a function that takes the n-bit string and outputs another n-bit string. It's a bijection permutation, and it's one way in the sense that if I give you pi of x for a random x, it's hard to find x, computationally hard. But of course, it's because it's a permutation, it's information theoretically defined. And then I will also use something else, namely a hardcore predicate h. And the hardcore predicate h is the following for this one-way permutation. It's a function that takes x and maps it to a single bit. And it has the property that h of x is pseudo-random, so you can distinguish, so you cannot predict it, even given pi of x. So think of it, I pick a random value n-bit string x, I give you pi of x, so you cannot compute x backwards. And then there exists this one particular bit, h of x, that is hard to compute even given pi of x. So you might have heard about the Goldreich-Levin hardcore bit. So it's defined that you take a random vector r, you take the inner product of x and r, and this will be your hardcore bit. The details are not so important, but just what you have to remember, okay, is that, pi is hard to invert, and h of x is pseudo-random. This one bit, h of x is pseudo-random given pi of x. Okay, so what do we know? What is the min-entropy of x given pi of x? So information theoretically, because p is a permutation, x has no min-entropy given pi of x, because it's determined information theoretically. But even what is the Hill entropy of x given pi of x? Actually, it has no Hill entropy either. Because if you give me pi of x, then there does not exist a distribution of high min-entropy that is indistinguishable from x. Because if you give me any candidate, give me x prime and say, oh look, this is x. I can, I apply pi, which I can do efficiently in the forward direction. I check if this pi of x prime equals to pi of x, and this will only be the case if x equals x prime. So I can efficiently distinguish every value from x, which means that x has no Hill entropy given pi of x. Okay, this, of course, same. Okay, so here is the construction of this counterexample. It's constructed as follows. Let's see. Okay, fix some parameter t. So this will be like some parameter, and think of it as in this experiment. So in this particular example here, t equals to 2, but the counterexample scales with t, and the bigger t we make, the stronger the counterexample will be. So we sample now a distribution xy as follows. First, we sample a uniformly random bit b. Flip a coin, bit b. Okay. Then we sample 2t inputs to the one-way permutation, uniformly at random, but conditioned on the hardcore bit of this h, h of a, conditioned on the hardcore bit of this 2t inputs to be the bit b that we just sampled at random. And then we sample another t inputs, but where the hardcore bit is the opposite, 1 minus b. No? So I sample a coin, E, then I sample inputs, I sample a random input, I look what is H, input A, I look what is H of A. If it's not B, I resample until I get 2T of them, then I get another T of them with the opposite bit. I have these bits A1 to A3T. Now I apply the one-way permutation to all these bits, PAI to PA, to pi of A3T, and then I sort them. So I just output them in lexicographic order. And this, this lexicographic, these sorted values of A1 to A3T will be my variable Y. Okay, what is X? X is simply this, the variable X will be simply this T values that I sampled, so this last T input. So here is like an illustration, right? I picked the random bit B. I picked the random bit B. I picked this 3T values, 4, so 2T of them have hardcore bit 1, here, here, and here, and 2 of them have 0, and they are in random positions because I kind of sorted them lexicographically, right? And the value X, the variable X, is simply the opening of these 2 values that have the same hardcore bit 0. Okay, let's look at these variables. What I claim is the following. Here's the claim. I claim that X, this variable X, conditioned on Y, has very high Hill entropy. I will tell you in a second why. So I claim that this X is indistinguishable from some variable that has high min-entropy. On the other hand, I claim that X conditioned on Y, and this single bit B, this one single bit, has no Hill entropy. So this one single bit destroys it completely. Okay, what is the intuition here? How do I prove that X has high, how do I prove, how do I prove that X has high Hill entropy given Y? To prove this, I have to, by definition, I have to come up with the distribution Zy, such that Z has high min-entropy, conditioned on Y, and Zy is indistinguishable from XY. So here is the distribution. I do the following. So this is Z will be uniform over this tuples here. I can define the following distribution. So I have this, this conditional part Y, and what I can do now is I pick any two positions that have the same hardcore bit, say this one and this one. And this will be like one particular point in this support of Z. Then I pick this one and this one, they have the same, this one and this one. So you see, if I do this, actually I get like 2 to the T, choose 2 possibilities to pick these 2 values. Okay? And I claim that this Z, if I give you random, so of course, so this Z has, there are many choices. It has, if I pick a uniform at random from this variable Z, it will have more than 2 to the possibilities, so it has min-entropy T. But on the other hand, I claim that it's indistinguishable from X. Why? Hand-wavy proof, because, okay, these are one-way permutations, and H is a hardcore bit. So even if I open these 2 values, so you have this Y, I give you these 2 values, you cannot tell if I really gave you these 2 values that had like the hardcore bit 1 minus B, or if I gave you like just pick any other 2 choices, and I gave you these 2 values, and actually when I sampled Y, actually I didn't pick the random bit B initially, but 1 minus B, and now I give you this uniquely defined 2 values that have this particular hardcore bit. You can't distinguish those 2 things, and you can reduce this to the security of the hardcore predicate. So if you could distinguish these 2 distributions, you could break the security of the hardcore predicate. On the other hand, once I give you B, once I tell you, look, this bit here is 0. So you know that, because it's 1 minus B. Once I give you B, there is no way for me to cheat anymore. I have to give you 2 values, and if I give 2 values, let's say these 2 ones, okay, I will apply pi. I will see if it matches these 2 values. If not, I know, okay, this is not X. But then I also check the hardcore predicate of these 2 values, and if it's not 0, I say, no, this is the wrong value. So giving this one bit kind of completely crosses out this entire choice down here of possible values that I could fool you, and the only thing that's left is like the original value X. So all the Hill entropy is gone. So I hope I gave you some intuition why this, what's going on here, how this one single bit can destroy everything. Basically, without this bit, there exists this huge huge support variable z, which has this huge support that everything looks exactly like this 1 point x, but once I give you this 1 bit, everything collapses to this 1 bit. Okay, so this is not... Okay, actually I'm done. Oh, actually, maybe because I still have 5 minutes, so why would I look at the, okay, I couldn't, like in Beamer you can't always compile stuff. If I compile figures and pictures, then it doesn't want to, so I have to. So what I do in the last 2-3 minutes is I will show you why is this chain rule that I showed you before, the conditional chain rule for Hill entropy, useful to construct leakage resilient crypto schemes. So this is from a paper of Eurocrypt 2009. And this is something that's called the leakage resilient mode of operation. So what is it? It's a mode of operation. So we have some function f. This function f takes a key k and some input y. And it's a pseudo-random function, which means that if I pick a random key k and you can query it, you can distinguish the outputs from outputs of the uniformly random function. In fact, I need something weaker. I only need it to be a weak pseudo-random function, which means it looks random if it's queried on random inputs, not adversarially chosen inputs. And this is just a mode of operation in the sense that, you pick 2 keys, k0, k1, and some random input y0, and then you can start evaluating this mode, right? I kind of take k0, y1, I get these 2 values, I apply these 2 values, I get these 2 values, and so on. And just without any leakage or anything, it's trivial to show that this sequence of values, y0, y1, y2, is a stream of pseudo-random bits. You cannot, if f is a pseudo-random function, this will be pseudo-random bits, so you can make this is called a stream cycle. You can just generate a very long sequence of pseudo-random bits and, for example, use it for encrypting using a one-time pattern. Now, in the leakage resilient setting, we actually want something much, much stronger. Now we anticipate an adversary who not only gets to see, so the standard definition would be the adversary sees y0 to say y4 or more, and he cannot distinguish the following bits from uniformly random bits. In the leakage resilient setting, we want something much, much stronger. Because now, what we do is, we allow the adversary to get leakage on the computation. So every time we invoke f, the adversary can first choose some leakage function f, so if capital F, some leakage function small f, we evaluate this function small f on all the secrets that have been used in this step, and the adversary gets this leakage lambda 1. Then he gets this leakage lambda 2. Then he gets this leakage, and so on. And what we want is that, okay, even if the adversary gets all this leakage and all these outputs, it's still true that all the values to be computed in the future are indistinguishable from uniformly random. What does this mean? This means that in practice, if you have like this stream cipher implemented on your smart card, the adversary kind of not only sees the outputs, but he also measures, I don't know, has some needles on the chip, he gets all this extra information. You still have the guarantee that whatever comes in the future will be pseudo-random. And this can be proven for this particular construction. And how do you prove this? So here is the proof. So first of all, we need a lemma that states the following: if f is a weak pseudo-random, function, so the output is pseudo-random if queried on a random key k and some public input y, then the output is still going to be pseudo-random even if the key and the input are not uniformly random as required, but only at high min-entropy. Right? So even if k just has min-entropy k minus some small lambda and the output n minus some small lambda, and the key and the input have to be independent, that's actually why this is this alternating structure here to ensure this independence, then you can still show that the output is pseudo-random. Of course, of lower quality. So if f is a very strong PRF and you leak a little, key and input are just high min-entropy, you lose something that is exponential in this entropy gap here. But it's still pseudo-random. So, okay, so how do we use the chain rule now? So we know that these values are uniformly random because they are initially chosen as the key. Now the adversary gets this leakage. Okay, so without this leakage, those values would be pseudo-random. But now the adversary has this leakage. So these values are not pseudo-random anymore, but they still have high Hill entropy. Because, and here we use the chain rule. Right, this is the chain rule. I told you, okay, x is pseudo-random, so x condition on this leakage has very high Hill entropy. That's where we use the chain rule. Okay, now so this Y has very high Hill entropy, so I can actually, in the experiment, I can replace it with something that has real min entropy, and the adversary will not be able to distinguish those two experiments. So now I'm in a new experiment, this Y is replaced with something that has high min entropy, and I continue this game. Now I have these two values, K1, Y1, they are independent. This is pseudo-random, leakage, Hill entropy goes down, I replace everything with min entropy, and I go on. So this was just to illustrate on a very hand-wavy level how this chain rule for conditional Hill entropy is used to prove security of leakage-resilient crypto schemes. Right? Okay, that's all. Thank you. Pseudo entropy to test. So how it would be applied to certify randomness? I'm not sure this is useful because here we always assume, okay, we have a variable that has some min entropy, but we never have to know what it is, or has some Hill entropy. We never have to, that's the entire point of the thing. We don't want to certify it, we just want to know, okay, if it's pseudo-random, and it leaks, we don't know in which sense it breaks or something, we just have like some very quantitative guarantees. And how to check if something satisfies this quantitative guarantee is a much more applied problem, I would say. We really have to look at this. So I don't see an immediate application to